Hello everyone. Today I'll be talking about my project for Mechanical Engineering 595R, and my topic today is EEG or electroencephalography imagined speech decoding with new proposed architecture. And that architecture is learning using statistical invariance. As a brief introduction to those not familiar with the space, EEG signals are a series of electrodes that are placed across the scalp, evenly spaced, to measure brain signals during various activities. It should be noted that EEGs are a non-invasive measurement technique, and we would not reasonably expect these to perform better than invasive techniques, which can often achieve much higher data fidelity and more direct reading of signals. The dataset that I'll be using today is Nieto et al. From 2022, where 15 subjects underwent many trials for each subject, roughly around 2,000 trials, on 4 separate words, these words corresponding to Spanish words for up, down, left, and right to move a cursor on a screen. And this is a common benchmark for classification of imagined speech in EEG signals. Now, for the state-of-the-art decoding performance or classification performance on this benchmark, we should understand that there are roughly 2 different ways to approach learning to classify imagined speech. One of them is using a general model, which works across many different subjects, and another one is to train a model per subject to deal with the idiosyncrasies associated with brain signals in imagined speech. Generally, we expect subject-specific models to perform better in classification accuracy than general models do. Now, these state-of-the-art architectures on this benchmark by Nieto et al. In 2022 are graph neural networks, state space models, recurrent neural networks, and convolutional neural networks, much of which we're familiar with from this course. For the architecture that I'll be proposing today, we're going to use a graph neural network. The benefits of graph neural networks are that they're readily interpretable, as different nodes in the graph are each going to correspond to different electrode channels that are placed along the scalp. And this is something that also further benefits us because EEG signals are commonly interpreted in terms of regions of electrodes, allowing us to focus in on certain of these node channels and ignore the rest as being unrelated to the activity of imagined speech. One issue that's common among almost all neural networks is the amount of data that is required in order to achieve good classification accuracy on a given task. And today I'll be proposing an architecture that helps limit some of the issues that come with the data hungriness of neural network architectures modernly. I'll be leaning heavily off of the following paper, which is the Complete Statistical Theory of Learning by Vladimir Vapnik and Ralph Ismailov from 2020. This is a paper I've been interested in for a long time, and I'm excited to finally have the opportunity to utilize it a little bit in this course. Now, in this paper, Vladimir Vapnik talks about utilizing both weak and strong convergence to minimize the required data set size by using expert loss functions, similar to how in a physics-informed neural network we might use physical laws in order to reduce the requirement of data sets or multiple expensive experiments. And now the further requirement that Vapnik imposes is that the residuals that we find in our model are orthogonal to the expert predicates or the expert requirements that we have. So the way that I'll be using this paper and this architecture broadly speaking is I'll be using both an out-of-the-box, state-of-the-art graph neural network that's pre-trained for tasks like this, and I'll also be using a custom graph neural network that I will train bespoke myself. We'll use some of the following expert predicates or known laws as far as neuroscience is concerned for imagined speech. Some of the laws, as we can see on the left, are related to areas in the brain and specific electrodes, which my data set does have data collected on. And they're associated with certain electrode channels that I'll be utilizing heavily in my training. some of the known predicates that we have are for Broca's area, dealing with signals in the gamma band, which is 30 plus hertz. We'll also be looking at Wernicke's area, also seen on the left, in the beta band, which is 13 to 30 hertz. In the motor cortex, we'll be looking at signals from 8 to 12 hertz, and we'll also be looking to see if more activity is being generated on the left hemisphere of the brain, as it's well known that lateralization does occur during imagined speech. So for the model architecture that we'll be using, we'll be pre-processing some of the raw time series electrode data into the frequency domain. We'll be doing that with Welch's method to get power spectral densities, and we'll be normalizing those power spectral densities using Z normalization. We'll then feed those normalized frequency domain features into a graph neural network that we will train using common graph neural network techniques. And then on the classification head of the graph neural network, where there's the possibility of 4 classes to be classified into, we'll also be using our learning using statistical invariance, or LUSI, regularization method, you can call it, in order to ensure that our residuals are uncorrelated from our expert predicates that we know, in order to ensure that our residuals are purely due to randomness in the data and that they're not related to our predicates. And so then our losses will have a cross entropy loss as well. We'll scale that LUSI term loss in order to then go through back propagation. And now some of the outcomes that we're hoping to see from this architecture is improved interpretability by directly relating electrodes to nodes in the graph neural network and hence to regions of interest. We're hoping to lower our data requirements by moving more towards one-shot classification. And then, of course, we're just hoping to achieve overall greater classification accuracy. And now we aren't necessarily seeing greater accuracy compared to state-of-the-art methods, but one thing that we are seeing in the runs that I've done is we're seeing that the methods with using the learning using statistical invariance tend to work better. In this case, for the general model that's trained on all subjects, we get validation accuracies around 0.3, whether I'm using raw time input or those pre-processed spectral inputs, whether I'm using in the box, out of the box, or a bespoke graph neural network. And for the subject model, subject-specific model, it's roughly the same outcomes, but just with a higher total validation accuracy of around 0.34 averaged across these different methods described in the last slide. And once again, this is lower than state-of-the-art performance. State-of-the-art performance generally hovers around 0.8 for validation accuracy for subject-specific models and around 0.4, 0.5 for general models. This graph here shows whether or not the LUSI method is working as we're expecting, and it's one of the more informative graphs on the matter. What we see here is a correlation heat map, where what we're checking for is if in my model that I have, my losses are correlated with these predicates in the left axis. And so ideally, in a system that is performing better, we will see values closer to 0, which inform us that our residuals that we have are uncorrelated with our predicates that we have, meaning that we're not leaving some information related to the predicates in the data set, in our residuals. And we see here for subject 1, where we end up using LUSI on the left and we don't on the right. The scaling's a bit off in the heat map axis, but we see broadly lower correlation for this subject when we use LUSI. But for a total comparison, what that looks like in losses over epochs and across all different subjects, we can see that for these LUSI networks, the LUSI penalty actually ends up being around 10th of that of the cross entropy loss that we have. So it's not a large effect compared to cross entropy, but we see that it does nudge the model towards having uncorrelated residuals. Now on the left, we can see the validation accuracy across epochs. For some subjects, it continues to increase throughout the training run. For some, it remains roughly the similar, and for some, it actually starts going down across the run. And this means that likely due to hyperparameter tuning issues, a sweep of which is out of scope for the purposes of what I wanted to do for this project, the architecture isn't quite working as intended to achieve state-of-the-art classification results. Now, going forward, I think that it's good to move further away from raw time series data. I think that injecting noise in order to learn more generalized features in the model is going to be important. I think a further utilization of frequency features will also be a good idea, using more tuned frequency features to EEG signals. And then I think further hyperparameter tuning and sweeps in order to prevent overfitting for things like weight decay, dropout rates, our LUSI penalty weighting, maybe increasing that would be important. But the important thing out of this presentation is that we can decrease the correlation of the residuals and our expert predicates using this method, which is hopeful for future use.